this section now we're going to combine what we've talked about with relational algebra and functional dependencies, and we're going to use that basis and apply a set of rules that is now going to help us start to do something really practical with what we've been learning. So I mentioned that relational algebra is the underpinnings of our SQL, right? So it's kind of the logic that we're following to work with our data. Functional dependencies are going to allow us to define how we're going to sort our data. And we haven't talked a lot about that yet. We're going to get more into that, especially as we talk about normal form coming up soon in the future. But for right now, we're still laying out the groundwork of how we actually get there. And one of the big things we've talked about is keys. Now, what we're going to do here is we're going to learn some rules that when we apply them, we're going to be able to use these rules to determine keys. So I have this slide up because one of kind of the messy examples that we recently worked through was this one where we had a star name added into our movies table. And we noted that this made for multiple kind of repeating data here, right? Like I have the movie Star Wars 3 times and 1977 3 times. Just because I had individual star names associated with each one of those movies. Now, again, we're not going to talk about the fact that it repeats yet. That's going to be something we're going to talk about when we start to normalize. But for right now, we even struggled to determine, all right, well, what is the appropriate key for this? So what we're going to learn now is the algorithm, so to speak. We're going to lead up to something called a closure, where we can determine, okay, so given a title, a year, and a star name, can I prove that I have a unique key that will give me a functional dependency for all of the other attributes like length, genre, and studio name in this relation? And that's what we're going to do now. We're going to start kind of pulling these pieces together and making that work. To do that, we're going to look at a few rules. We're going to start with a splitting and combining rule, which is pretty simple. It's just going to be some fundamentals on how we can pick apart functional dependencies and build them back up. We're also going to look at what are called trivial and non-trivial functional dependencies, and also completely non-trivial. That's going to lead us to the transitive rule, which we're going to apply to kind of create new functional dependencies out of existing ones. We'll explore that, and we can combine all of these things now to determine what's called a closure. And the closure is going to get us to determining those keys. And that's really where we're going to kind of stop off. Once you have closures, you can kind of look at, like subsets or projections of a relation to see that closures actually, apply to certain things, and then determine the minimal key. And that's where we're going to kind of leave it. So let's start with splitting and combining. So this is pretty straightforward. Basically what we're saying here is that if you have a functional dependency, a set of attributes A, and you have a set of attributes B, and they're functionally dependent on each other, you can break down the right side, if you use the splitting rule, into smaller right sides. Usually it would be a single attribute on the right side, but you have to leave intact the original A set, right? So, say if there's like 2 attributes in set A, say it's title and year that we're using in the movie one, you don't have to have genre, studio name, and I think producer C was one of the ones over there at one point. You don't have to have all of those in B. You can break it up and have them on separate functional dependencies here. So title and year can equal studio name. Title and year can be the functional dependency for producer C. Title and year can be the functional dependency for genre, right? So you can break that apart, but only on the right side. The left side has to remain the same. The opposite of this is the combining rule, and it's pretty straightforward. You just take what we have here in the second grouping, where we have the set A1 through AN is functionally dependent for B, you then combine B back into what you see above it, and you end up back where you started. So splitting and combining rule are just the same thing, going two different ways. Now, what's important here is that you cannot do this on the left side. So let's move to a more concrete example to explore that. So we can, using the combining rule, now take title and year, length, genre, and studio name, those three individual functional dependencies, and combine them into one, where length, genre, and studio name are functionally dependent on title and year. But we cannot break apart the left side. Let's see what happens if we try. So imagine we have title and year. We break it up into two different functional dependencies here. Length is not functionally dependent on title. Now, you could maybe make an argument for this, but your argument would be based upon what we decided was our key previously, which was the combination of title and year, right? So the length of a movie is not necessarily dependent on the title. There could be a world in which there are more than one movie with the same name and different lengths, right? Or at least I believe so. I'm not a movie exec. So this is not a valid functional dependency. And the second one here illustrates that even better, because this one would imply that every movie made in the same year was the same length, and we absolutely know that's not true, right? So that one is blatantly obvious. The first one is definitely not true, but it's a little bit more circumspect to argument based upon what makes a movie unique. Which is something we're going to discuss at length coming up in future talks. But for now, we're going with title and year because that's what we're doing here, and title alone is not enough to determine length. So let's now talk about a trivial functional dependency versus a non-trivial or completely non-trivial one. So a trivial functional dependency, all that means is that the right side of the functional dependency is a subset of the left. That's it. So basically what we're saying there is if you have title and year on the left, title is a subset of the left side on the right, right? If it can be just a subset, or it can be as a representative of the whole set. You can have title is functionally dependent on title, and that is a trivial functional dependency. This is trivial because we can always assume it's true. That should make intuitive sense, right? It would be like if we went back to our previous talk and we said that your average, your grade is functionally dependent on your average, right? So if you have an average of 97, your grade is an A, right? That is always going to be true because those two things are intrinsically linked, right? So if that is the case here, this is a trivial functional dependency. If you say that a title is functionally dependent on title, of course that's true. We don't have to prove it, right? That is absolutely true. So the point of kind of describing a trivial one is just to kind of get to the point where we can get to this, which is a completely non-trivial one. And now we'll know why we have to break these things apart, because this is the one we actually are looking for. So those things we don't care about. Those are simple, right? But for completely non-trivial, and I'll explain why it's completely in a moment, functional dependencies, there is no subset of the left side on the right. So in this case, we have title and year on the left, and we have length on the right. Title or year do not appear on the right. This is a completely non-trivial functional dependency. This is the one that we want because these are the ones that we can now use to describe what we care about, which is how do we find a key that describes all the other attributes, right? So this is all the other attributes. That's what we're looking for. Now there's a middle ground here, and this is important because now we can use what we were just discussing here with splitting and combining to get to trivial and completely non-trivial. So if you have a non-trivial functional dependency, that means in this case we have title and length being dependent on title and year. Now notice title appears on both sides, but length does not, right? So this qualifies as a non-trivial. We can split now this. Remember, the left stays the same, but we can split the right now, and we can say, okay, well, title and year for title being functionally dependent on title and year is trivial, so we don't care. But length being dependent on title and year is completely non-trivial, so that one is interesting to us, right? So now we can use splitting to break apart a non-trivial one into completely non-trivial and trivial. And we also now have some rules that we can apply for trivial dependency. So this one's very straightforward, so I'm just going to kind of look at it quickly. Again, we're showing sets here, so I'm going to give a real example in the next slide. But basically what we're saying here is that if we have, B, a set of attributes B is functionally dependent on a set of attributes A, then it logically follows that the set of attributes A unioned with B is also functionally dependent on A. And this makes sense because it's reversing what we did here, right? So if you have non-trivial, you have a combination of trivial, which is in the left side, and things that are not, right? Which is exactly what we're showing here. A is on the left side, B is not. So this follows suit from here, and it's just an abstraction of it. And you can also say that it is also true for the intersection. So if I have the intersection of set A and set B on the right-hand side being functionally dependent on the left, that is also true because the intersection is really just a smaller subset of the union, right? So that is obviously going to be true as well. Now, what we really care about, though, is this. This is the transitive rule. So the transitive rule says that if I have a set B that is functionally dependent on a set A of attributes, and I have a set of attributes C that is functionally dependent on a set B, then I can also say, and this is important, that I have set C is also functionally dependent on set A. We didn't explicitly say that in the definition, but we can imply it. So this now allows us to combine functional dependencies in order to get new functional dependencies. This is going to be the mechanism by which we can evaluate all of our attributes in an algorithmic way in order to determine which ones are, say, dependent on a key versus which ones are not. And that is now going to lead us into closures, which we're going to get to in a moment. Let's look at an example quickly of the transitive rule before we move on. So here we have studio name being dependent on title and year, and we have studio address being dependent on studio name. So we can now say with the transitive rule that studio address is also dependent on title and year. Now, how did we come to that conclusion? We'll just follow it through, right? Studio name is dependent on title and year. And, imagine back when we were going through functional dependencies and we said, if you have row A, row B, or attribute B is dependent on attribute A, that means that if A is, one value, then B has to follow suit. And now we're saying that attribute C is dependent on attribute B. So if attribute C is one value and attribute B, they have to follow suit. So that means that you can say that A and C also follow suit because you can just draw the line right through. So now we can use this to kind of build additional sets of functional dependencies that we can use to determine keys. And we're going to do that with this rule. Well, it's more of an algorithm really called a closure. So what we need to do this is we need a relation that we're testing against, right? We need an initial set of attributes that we want to test for the closure for. So for our Star Wars example, not Star Wars, our movies example, we would have title and year or title, year, and star name, depending, as a set of attributes that say we wanted to test against. Say we only had title. As you'll see, that would not be enough to create a proper closure. And we'll see that, but we're actually going to see now how you can take a hypothesis, basically, of what a key could be, and then use the functional dependencies to prove or disprove that that is in fact an inclusive key. So that is what the idea is here. we're going to find all of the attributes B such that the set of initial attributes, the ones that we're passing in, such that B is functionally dependent on that set. And just so you know, the way that we're denoting this here is with the list of attributes and then the plus sign after. That represents that it is a closure. You'll see it when we finish some examples. So let's take a look at the algorithm. So as input, we have our set of attributes that we're testing and a set of functional dependencies, which we're going to call S. The output is also going to be a set. It's going to be the closure, and I'm often going to refer to it as X. So you'll see it as we go through here. You'll see X equals, and that's going to be representing the output set. Same like S, you'll see S equals, and S is going to be representing the functional dependencies. Now, as I go through, you'll see that I might like remove functional dependencies from the set as I go through, and that's more or less just to kind of like note that we've been through those. It's not that they necessarily get removed, but you'll see as we show here in step 4 that you have to repeat until no more changes happen. So I'll point that out as we go through, but it's just my effort to kind of like remove the ones that are done so we don't have to think about them again. So basically what we're going to do here, here's the process. So we have our input and our output. The first thing we're going to do, and this is a good thing to do, but it's not always absolutely necessary, is we're going to use the splitting rule, and if we have any functional dependencies that come in set S, and they have multiple attributes on the right-hand side, we're going to break that functional dependency up using the splitting rule until we only have one attribute on the right-hand side. So in our first example here, we have AB, well, CD is functionally dependent on AB. So that's going to become two different functional dependencies. It's going to become C is dependent on AB and D is dependent on AB. This is just to keep things nice and simple as we run through the algorithm. The second thing we're going to do is initialize our output, our set X, and we're going to initialize it with the input attributes. So if we were testing this for title and year, like I mentioned before, you would automatically put title and year into X before you even run through the algorithm at all. Then for each functional dependency, so now imagine that we're going to enter a loop, and we're looping through the set of functional dependencies. So for all of you object-oriented programmers out there, imagine that I have a list of type functional dependency, and I'm going to have a for in loop, and I'm going to loop through this list, and for each iteration through the loop, I'm going to look at one of the functional dependencies, right? So for each functional dependency, I'm going to look at the attributes on the left side, and if they are all, that's the important part, all in X, then whatever attributes are on the right side are going to be added to X. All right, so we'll see that happen. So basically we're going to grow our X as we loop through here, and we're going to keep doing this until no more changes happen. So I have a few examples here that I want to run through. The first one here is right out of the book. The other ones are kind of derived from it, but not the example. But I want to go through this one first, so if you've read through it, then you can kind of follow along with this one, and hopefully it helps reinforce it. So basically here what we're saying is we have a closure of A and B. That's what we want to test for. Remember, these are the two, in this case, two attributes. It does not have to be two. In this case, it's two. These are the attributes that we want to test for. The relation we have, the entire set of attributes that we're going to be working with, has attributes A, B, C, D, E, and F. Now, so our input is the attributes we want to test for and the functional dependencies that we are going to use to test. So the set of functional dependencies, remember we're referring to that as S. For us, it has C being functionally dependent on AB, AD being functionally dependent on BC, E being functionally dependent on D, and B being functionally dependent on CF. So we're going to now first apply the splitting rule, like we mentioned before, on AD being functionally dependent on BC. So that's going to break that up into two individual functional dependencies. So now we have A being functionally dependent on BC and D being functionally dependent on BC. The second step, now we're going to initialize X, like we said, with the attributes that we are using to determine the closure. So that is A and B. Right? So our X does not start empty, and that should be A comma B. Sorry about that. I'll fix that. Our next X does not start empty. It starts initialized with the ones that we pass in. Now, the next part here, we're going to look at each functional dependency. We're going to enter that loop in our set S and determine if we can add the right side to our X. So what we're looking at here, if you look at the first non-indented line, I have the current set of X. So think of this as like you stop the debugger, in your loop, and you look into memory and you see what's going on, right? So in memory right now, before I actually complete this iteration for the algorithm, my X started initialized with A and B. My set, now remember, this is the part where I mentioned I'm going to be removing things from this set, but that's really for our just clarity. There's really no reason you can't. Once you've used it, you can remove it, but it's not really that it's technically removing it from the set. It's just that you're done with it. So for our purposes, as I get through things, I'm going to remove them from the set so we can see what's left a little bit more clearly. So the first loop through, I'm going to be looking at ABC. So you see that I pull that functional dependency out and I put it into the indented line. And then we say, okay, so A and B are both in X. So remember, we evaluate the left side of the functional dependency against X. And if both, or I shouldn't say both, if all of the attributes in the set are also in the set X, then we can add the right side. So right now, C is what's on the right side, and we can go ahead and add it because A and B are both in X. So now, on, say, the start of our next iteration, X is now including C, and our S set has changed a little bit. We've removed that first functional dependency. So we check the second one. A is functionally dependent on BC. Well, let's check that. So BC, both of those are in fact in X, but it doesn't really matter because A is already in X, and we don't add A more than once. Think unions with set logic. That doesn't need to happen again. So we're going to move on there, and we're going to go to the next loop. This time we have X is still A, B, and C. We're short one more functional dependency there, and we're evaluating D being functionally dependent on BC. BC are in fact in X, so we can add D. So we do. So now we're down on the next loop. Now we have A, B, C, and D in X, and we're checking E being functionally dependent on D. D is in fact in X, so we can go ahead and add E, and we do. And now we're on the last iteration here. So now for this last iteration, we have X with A through E, and we're testing B being functionally dependent on CF. Now, C is in X, but F is not. So we don't add B, but not that adding B would have mattered because B was already in there. But note that F was never something on the right side to get evaluated. What's important here is that, like say B had been something else, like B had been G, right? And say we change this and the initial relation had A, B, C, D, E, F, and G. G would not have been added here either, right? It's just that B just happens to already be in the set. But what's important here is that whatever was on the right side was not going to be added or re-added, not that that would have mattered, because F was not part of X, right? So the left side was not a subset of X. So our final answer here is that X is equal to A, B, C, oops, that's supposed to have an E in it, A, B, C, D, and E. And S is now empty. So it does look like I have it right over there, but on on the left side of the bottom of the slide, that's supposed to be A, B, C, D, and E. But on the right side, now we're looking at our closure for A, B, and it's equal to A, B, C, D, and E. Notice that it does not have F in it, though. All right, so that's the book's example number one. So what were we doing here? Like, what was all this accomplishing? So we're using the splitting rule, because remember we used that at the beginning to break up functional dependencies that did not have a right side of just one attribute, right? We're using the combining and transitive rules now to determine the closure. So, if you look at what we're doing here with the transitive rule, we're seeing, okay, so, this is very similar to what we were saying before. Like if you have, B being functionally dependent on A and C being functionally dependent on B, A or C is functionally dependent on A, right? That's what we're doing here. We're taking a attribute and we're evaluating it against the attributes that have already proven functional dependency, and we're saying, okay, this falls into that same thing, and we're having an algorithmic way now of adding that into the set. So basically what we're doing is we're taking care of those transitive dependencies by actually using an algorithm, right? So this now allows us to hopefully do something more real. And I already kind of alluded to this, right? And I know this is all, a lot of just kind of might feel like a lot of work, but what we're actually doing here is laying down the foundation so that you can determine a key, right? Which is a fundamental thing that we have to do. So let's look at another example. This time, instead of just using letters, though, let's actually use actual names for our attributes, right? So we're going to pick on a working version and a non-working version to contrast them. So here is our Star Wars closure example. This one is based on one of the earlier Star Wars tables in the book. Or I keep calling it Star Wars, but Star Wars on the brain. But it's the movies relation. And what we want to do now is determine if we say, our theory is that title and year would give us a closure on the whole relation. Let's test that. So our inputs going into this are going to be title and year for the attributes that we want to test for closure, and we're going to have functional dependencies as follow. Just looking at this, we can kind of determine that studio address is dependent on studio name, length is dependent on both title and year, film type is also, there was a comma there, so length and film type are dependent on title and year. And studio name is dependent on title and year. And before we even go any further, I just want to point out, if you look at this, you can kind of see the transitive dependency piece, because look at the first one, right? So studio name and studio address, if anything, like when we get into normalization, you'll see like that's probably supposed to be somewhere else. But that aside, for right now, those two things, while being dependent on each other, seem to be, a little kind of away from the rest of the data. The rest of the data is more about the film, and these two things are more about the studio, right? But then we say, okay, so title and year, they are the two things that are going to give us our length, film type, and title year. Okay, our length and film type, sorry. And then title year is also title and year are also going to give us studio name. So that gives us, that same thing we were looking at before, where B is dependent on A and C is dependent on B. So yes, you can say that C is dependent on A, right? So this is just a fancy way of getting us to that same conclusion, but with an algorithm, so we can make sure that we always pick up all the pieces. So let's look at this and let's play it out. So X starts out with the two attributes that we are doing this against, which is title and year. And our first functional dependency that we want to test against is studio address being dependent on studio name. Now, notice that studio name is not in X, so we're actually going to skip this one. But this is important. I'm not going to remove it from the set, so to speak, of S. All right, I don't even have that on this slide. I decided not to clutter it up this time, but I do want to note that just because we weren't successful in using it, it didn't get removed from the set. We are actually going to want to revisit this one, and we'll see why in a moment. So now let's move on. So X hasn't changed, it's still title and year. This time we're looking at the functional dependency of length and title year though. And that is true. Length is dependent on both title and year. So we can add length. So now we have title, year, and length. We're going to do the same thing for film type. Film type is also dependent on title and year. Title and year, as before, are still in X. So we can go ahead and add film type. And now we're going to look at title, year, and studio name. Title and year are in fact still in X, so we can add studio name. Now, what's interesting here is that if we go back and reevaluate the first one that failed the first time through, it would succeed now, right? Because remember, that functional dependency only required studio name for studio address, right? And now studio name is in X. So if we go back and we reevaluate it, now we can add studio address. So this is a successful closure. We have attributes title and year, closure representing all of the other attributes: title, year, length, film type, studio name, and studio address, right? So this was successful. This is a key now. So we can use our closure to determine if a set of attributes in a relation is a key. And this is obviously going to be important for all of our work with relational data stores. Now, let's look at a different one. Let's look at one that it didn't quite work out, right? So this is now the one with star name. Now, the important thing here is that if we do this with our original algorithm, with just using title and year as our proposed key, you can see there's no functional dependency that would work here for star name. But if we say that we use title, year, and star name, now it will work, right? Because star name on its own had no other functional dependency when we start with a set of title and year that would add it to that list. But it will work if you have it in the initial list. So that is how we had to work up to a key that actually included everything, right? So that is, and we're going to talk about that more in a moment as far as like where you start and how you build up. I invite you to, try this and work through it. It should be pretty easy to kind of go from here and work through it, on this one. But it's a good exercise, and it makes sure that you've got it in your head exactly how this algorithm is working and how it produces results. So now that we know how a closure works and what it produces, how do we go about making sure that we can use a closure to find all the keys, or hopefully maybe a minimal key? So let's talk about that a little bit. We can obviously test every subset of attributes in the relation. This is going to be extremely tedious. So if we just go back and we look at this one, we'd have to test title. And then we'd have to test year and length, or maybe we test title, and then we test title and year and length, and title, year, length, and genre. Now, if we had tested title and year in the first one, we would have hit success right there, and we would have been done. But this is the one with star name. So if we did that, so let's say we do title first, title, year, no, that's not going to work. Title, year, length, not going to work. Title, year, genre, not going to work. Title, year, length, genre, studio name, not going to work. Title, year, length, genre, studio name, star name is going to work. Every iteration of all of the attributes should work, because if you have two tuples in there and your key is every single attribute and they're the same, then that's invalid, right? So if you have every attribute as part of the key, it's automatically unique. That said, obviously we know that the real one we want is what's called the minimal one, which is title, year, and star name. It is a fact that once you have title, year, and star name, any combination beyond that, if I have title, year, star name, and studio name, it is still going to be unique. It is just not the minimal key, right? So what we want to do is find that minimal key. So the easiest way to do that is, instead of just kind of arbitrarily doing it, what we're going to do is we're going to start with the smallest set size of attributes. So we're going to initially do just individual ones. So title, okay, didn't work. Year, didn't work. Length, didn't work. Genre, didn't work. Studio name, didn't work. Start name, didn't work. Okay, now we're gonna do combinations. Title and year, didn't work. Year and length, doesn't work. We're gonna go through that. Eventually, we'll get to combinations of 3, and that will lead us to title, year, and star name, and that would be our minimal key. So that's the idea here, is that obviously this isn't the most efficient way to do it, but usually a well-designed table is not going to be leading you down all these crazy amounts of keys. Most of the time in the real world, you're going to be working with 1 or 2 attributes that combine to make a key, and using this will find it relatively quickly.